Chapter 4 is a big chapter with a lot of concepts, new terminology, and it's a massive chapter. So I decided to cut it in pieces and regroup sections by similar topics. That's why you see here that we will now see some pieces of 4.1, 4.2, 4.4, and 4.5. So now what we want to see is the notion of linear space. So we are in linear algebra. There's something about linearity. So we want to see what the linear space is. In your book, they also use the expression vector space, which is fine. So you can use whichever one you like. Vector space or linear space, it's up to you. Most of the time I will use linear space because the main property here is linearity, so that's the reason I'm going to use linear space a lot. We are going to see what is a subspace, so linear subspace. Well, that's not a big deal, it's just, let's say, a subset that is also a subspace. So it's just a smaller space if you wish. And then we are going to see the notion of span. So this is a buzzword. We will see what is span. It's not a big deal actually. Let's say you have two vectors u and v. Span of u and v is a set that you get when you put together all linear combinations of u and v. So you have a set of linear combinations of u and v, all of them together. That's called span of u and v. So that's nothing special. Then we will see the notion of a basis for a linear space. And the thing that is linked to the basis is dimension. So dimension of a linear space is just number of people in a basis. So we need to see what is basis actually. So those are the concepts that we are going to go through today. Basically the definition of a linear space, some examples of linear spaces, and some examples of what is not a linear space. And then we will see how to create linear spaces using linear combinations actually, so that's span. And then we will see how to find a basis for a linear space. And once we know how to count how many people are in the basis, that's a dimension. So I will start with some examples of a linear space. So pretty much everything you know up to now was a linear space, but there's some particularity here in the way I write it. So real numbers with operation of addition and multiplication by a scalar. So this thing here is a linear space. So this is some artistic way of identifying addition of operation of addition of numbers, and this is some artistic way of identifying multiplication by a scalar, by a number, by a constant. So basically real numbers with standard addition and standard multiplication by a number, that's a linear space. And then R2, so the vectors with two components, with standard addition of vectors with two components. So we add corresponding entries, and standard multiplication by a number. So we multiply every entry by the same number. Well, this triplet here, so the block here you see, that will be also a linear space. R3, so the vectors with three components, with standard addition and standard multiplication by a scalar, that's also a linear space. Vectors with n components with standard addition and standard multiplication by a scalar is also a linear space. So you see what's happening. I have a set, here R3, let's say, that contains objects, in this case vectors with three components. And then I have an operation of addition, how I add objects, how I add vectors with three components. We already learned that. And how do I multiply them by a constant? We also learned that. So those are the operations that I need on my objects, on the vectors here with three components. I need to be able to add them, and I need to be able to multiply them by a scalar, a constant. So once I have those rules, well, these three things together form a linear space when these two rules of addition and multiplication satisfy certain number of conditions. But what is important to realize is linear space will be a set with these two operations defined, and these two operations need to satisfy certain number of properties. We will see that. Other type of linear spaces, so linear space is not just a column of vectors, it could be also matrices. So matrices 2 by 7, 3 by 11, 2 by 2. So set of matrices with addition of matrices as defined, standard addition, and standard multiplication of a matrix by a number, by a constant. So this thing here is, so these three things together form a linear space. Polynomials, so I can have polynomials up to degree, let's say 5 or 10 or 11, doesn't matter, with standard addition of polynomials that you learned in high school and multiplication by constant. So this triplet here is also a linear space. Functions, so sines, cosines, exponentials, so space of functions with standard addition and multiplication by a number, well, that also forms a linear space. And also I can have functions that have first derivative continuous or second derivative continuous or fifth derivative continuous. So all those sets with classic addition of functions and multiplication by a scalar, they also form a linear space. So actually pretty much anything you know up to now is a linear space. So it's a set of objects on which we define addition of objects and multiplication of each object by a scalar, by a number. And these properties, these operations need to satisfy certain number of properties. So up to now everything you know is actually a linear space. So formal definition of a linear space, so what we need is a set of objects, non-empty, on which we define two operations, addition of objects and multiplication by a scalar. In our case it's going to be real numbers. And those two operations need to satisfy certain number of rules. When they do, then we call that set with those two operations a linear space. So here are the properties or the axioms that addition and multiplication need to satisfy. So first 5 are related to addition of objects, addition of vectors, let's say, or matrices or functions or polynomials. And the properties from 6 to 10, they are concerned with the multiplication by a scalar. So we don't need to verify all these properties. We don't need to remember them. I will just point two important properties. The property number 1, when you have two objects in a set, when you add them, the result is supposed to be also in the set. So if I have two vectors of two components, I add them, what I get as a result is also a vector with two components. So we want some type of predictability. And the property number 6, what it says, you take an object, so let's say a vector with 3 components, and you multiply it by a number, so the result is also a vector with 3 components. So those are the main properties that we will use, and those properties assure linearity actually. All the others are things that you already are familiar with, even though you were not aware of it. We don't need to remember them, we don't need to verify them. If somebody was defining a new way of adding vectors or new way of multiplying vector by a constant, then those people would need to verify all these conditions. We will not do any of those. This is just a list for you to be aware of what are the conditions. And again, the two important ones are addition. So this is called closed under addition, and multiplication by a scalar. This is called closed under multiplication. So this is another way of saying the same thing with a lot of more words. So what is important to observe here is that we will deal with real linear spaces or vector spaces. It's about the constant. When we multiply by constants, our constants will be real numbers. So that's why we call it sometimes real linear spaces, but we suppose that we are dealing always with real numbers, so we don't need that specification here. The element 0 for addition, it doesn't need to be a number 0. We saw that we can have vectors, so it could be a vector full of zeros, or a matrix, so matrix full of zeros, or a function, so function 0 or polynomial 0. So when we write 0, it depends on what is the set on which we are working. Is it a set of vectors or matrices or functions? For us in the course, we will just focus on vectors, but you need to know that these notions are very general, so they can be applied to other things. But for us, it's going to be just vectors, columns of numbers. So in general, the objects are not necessarily columns of numbers, as we said, can be matrices or polynomials or functions. But for us, we are going to work only with columns of numbers. So if we wanted to verify that a certain set is a linear space with given addition and multiplication, we would need to verify all 10 properties. So it would be a work for 10 small proofs. We are not going to do that, but if somebody was requested to do it, that's what that person should do. It's a lot of work, so we are not going to do that at all. It is normal that if one of those properties is not satisfied, then we know that the set with those addition and multiplication is not a linear space. But again, we are not going to do that at all. In general, what people do, they make sure that their set has at least one object inside. So most of the time we verify, let's say, that 0 is inside, and we will see that every linear space needs to have a 0. So 0 is super important element for any linear space. And then we verify the addition and multiplication by a scalar, basically closure under addition. When I add two people from the set, do I get the result also in the set? And multiplication by a scalar, if I multiply somebody from the set by a number, is the result also in the set? So those are like the two main verifications, and then there are all the rest. So somebody who would need to verify if something is a linear space from scratch would need to verify all 10. We are not going to do that at all. The important part is these three properties here, because this is what ensures the linearity of linear space actually. So we say subspace. Subspace is basically a subset that is a linear space. So it's just a vocabulary. You can even forget about sub, just call it linear space. It doesn't matter. So if I have a subset of a linear space and I have the operation of addition and multiplication that is already defined, and we are going to use only the standard ones, we are not going to invent anything new, then H will be a subspace if and only if all of the three conditions are satisfied. So 0 vector needs to be in H, so it's super important. If I have two people from H, U and V, if I add them, the result should also be in H, so this is closure under addition. And if I take somebody from H and multiply by number C, any real number C, the result also needs to be in the set. So when I have all of these three conditions satisfied, I will say that H is a linear subspace of V. Basically, H is a linear space. We are not going to do that now. We will have a special session just for this. So this is just for you to know what is the procedure in general, and that these three properties actually ensure the linearity. That's the main goal here. So those properties ensure linearity. Every subspace is actually a linear space, and every linear space could be seen as subspace of itself or some other bigger linear space. So these are just terminology. As I said, you can subspace, technically you can use it. If you don't wish, it's fine. You can just say linear space is just fine. Some examples of linear spaces on top of those given already. So we said every linear space is also a subspace. We have a zero subspace. That's a very special one. It contains only element 0. So let's say I have V is R2. So element 0 is vector 0, 0. So a set, so this is a notation for a set with these curly brackets. Set containing 0 is actually a subspace. It has only one element, 0. And it is a subspace. Well, this is actually the only linear space that has one element or a finite number of elements. Every other linear space will have infinitely many people inside. Another example of a linear subspace, so if I have a homogeneous equation, ax equals 0, and I consider only solutions for this equation here, so solutions for the homogeneous equation, they form a linear subspace. We will later see how we verify it. Basically what we do is verify these three properties. That 0 is there, obviously it is. If I add two solutions of a homogeneous system, I get another solution of a homogeneous system. And if I have a solution of a homogeneous system and I multiply it by a number, any number, I will still have a solution of a homogeneous system. So that's how we will do in another video. Another example is diagonal matrices n by n. They form a linear space or linear subspace of matrices. Symmetric matrices n by n. So obviously matrices n by n, there's a lot of them, and symmetric matrices are very special. So that's why you can say, okay, symmetric matrices are a subset of n by n matrices. You see the difference? And those matrices form a linear subspace. So these matrices form a linear space actually. Triangular upper matrices form a linear subspace. Triangular lower matrices also. Matrices n by n that have entries, diagonal entries equal to 0, they form a linear subspace. And let's say vectors in R3 that are orthogonal to a given vector u in R3, those vectors also form a linear subspace. So we have different types of linear spaces. Some examples of sets that are not linear subspaces. So solutions of ax equal b. So I have a non-homogeneous equation. Solutions of ax equal b, that's a set of solutions when they exist. And this set is not a linear subspace. One of the easy ways to verify that is just to check if 0 belongs to that set. Well, 0 doesn't belong because a times 0 is 0, it's not b. So 0 does not belong to the set of solutions of ax equals 0, or ax equal b. So the set cannot be a linear space without 0. Every linear space must contain 0. So that's why the condition of verifying if 0 belongs to the set is super important, because 0 needs to be in every linear space. So here 0 doesn't belong to W, so W cannot be a linear space. So it cannot be a linear subspace. So that's the same thing. So if I have n by n matrices that are invertible, that's a set of matrices, they are special, they are invertible. This does not form a linear subspace of n by n matrices. Why? Well, again, matrix 0, square matrix 0 is not invertible. So the matrix 0 does not belong to set of invertible matrices, n by n. Therefore, the set of those matrices cannot be a linear subspace, obviously. Some more particular example, if I'm in R2 and I have vectors of form 2t with t real numbers, so let's say 2, 0, 2, 1, 2, 7, 2, minus 11, so that's a set of vectors. Obviously, vector 0, 0 doesn't have the form 2 something because it is 0, 0, it's not 2 something. So vector 0, 0 from R2 does not belong to the set of vectors of the form 2 some real number. Therefore 0 is not there. So if 0 is not there, the set cannot be a linear space. Very simple. Another one, here if I have a set in R2, so the vectors with non-negative components. So components of vector x, y, x is positive or greater or equal 0 and y is greater or equal 0. So in this case, vector 0, 0 belongs there. That's fine. And even if I add two people from the first quadrant here, so with first component greater or equal 0 and second component greater or equal 0, if I add two vectors, the result will also have first component greater or equal 0 and second component greater or equal to 0. So in this case, I have 0 that belongs to the set, and set is even closed under addition. Beautiful. But if I multiply anybody from the set by a negative number, they will jump out of the set. So if I have here red circle some element in the first quadrant and I multiply it by -1, so I have negative of each component, I'll find him here outside the quadrant. Well, that's no good. It doesn't preserve, it's not closed under multiplication by a scalar, so it doesn't preserve the elements inside the first quadrant. Similarly, if I take somebody on the x-axis and multiply by -1, I'll get somebody outside the first quadrant again. So this set is not closed under addition, is not closed under multiplication by a scalar, even though it is closed under addition and 0 is there. But unfortunately, it's not closed under multiplication by a scalar. Therefore, this is not a linear space. We will need the notion of linear combination, especially for the span. So this is just a reminder what is a linear combination of vectors. Well, it's basically a summation of scalar multiples of vectors. So W is linear combination of v1, v2, vk, when W can be written as c1 times v1 plus c2 times v2 plus ck times vk. So it is a summation of scalar multiple of vectors. That's a linear combination basically. So we can create a linear space using linear combinations actually. So let's say I have vectors v1, v2, vp, certain vectors, span, so your new buzzword, span of those vectors is a linear space that is created or generated by all possible linear combinations of v1, v2, v3, vp. So I take all linear combinations, so all vectors that can be written as linear combination of v1, v2, vp, and I put everybody together in one set, in one big bag. Well, that bag forms a linear space. And that space is called span of the vectors. So if I have, let's say, vectors u and v, span of u and v is the linear space created by all linear combinations of u and v. So number times u plus number times v. So I put all of these linear combinations into one big bag. That bag is called span u and v. So the span of the vectors contain all linear combinations of those vectors. And it is a linear space. So now if I have a set of vectors, okay, and I take them from a linear space somewhere, I will say that that set generates, creates, or spans the entire linear space if and only if every vector in V, in the big space, is actually a linear combination of vectors in S. In other words, V is actually equal to span of those vectors. So then we can say that the set S spans or creates linear space V. And again, span is just linear combination of vectors. That's all it is. All linear combinations put together, and it's a linear space. We have already seen a question regarding linear combinations. We say, is Z, a vector Z, a linear combination of vectors u, v, or w? So now we can ask the same question in a different way. Just say, does Z belong to span of u, v, and w? Because span is set of all the linear combinations of u, v, and w. So Z is linear combination of u, v, and w if and only if it belongs to the span, obviously. How do we verify that? But the same way as we did for linear combinations, we need to solve a non-homogeneous system. If this system has at least one solution, that means if it is consistent, then indeed Z is linear combination of u, v, and w, so Z belongs to the span of u, v, and w. Obviously, if this non-homogeneous system is not consistent, therefore it doesn't have a solution, then Z is not a linear combination of u, and v, and w, so Z does not belong to span of u, v, and w. Now, just because we introduced the new name span, we have a different way of asking question about linear combinations, because span is just a set of all the linear combinations of u, v, and w. That's all it is. So let's see some special span spaces. So if I have a vector 0, I can create a span, obviously. All linear combinations of vector 0. So 0 in Rn. Well, that creates a 0 space called span of 0, 0 space. It's space of all linear combinations by definition of vector 0. But what are the linear combinations of vector 0? It's a number times vector 0. Well, that gives vector 0. So we know that already span of any vector is a linear space, that's fine, but this linear space is special. It has only one element, vector 0, because any number times 0 is 0. So span of 0 is just vector 0. So this one is special. So 0 space is the only linear space that has finite number of vectors. Actually, that has only one vector. Every other linear space will have infinitely many objects inside of it, but this one is very special. So that's why we talk about it. If I have a vector 1, 0 in R2, span of 1, 0, what is it? It's a set that contains all linear combinations of vector v. Vector v is here, 1, 0. So this is, by definition, span is a linear space, but how does it look like? Well, 1, 0 is somewhere here. So it's any number times 1, 0. So when I run through all the real numbers, all the values of C, all real numbers, I'll get this line here, blue line. So this is a straight line that goes through the origin. Very important. Every linear space needs to contain the origin. Always. So span of vector 1, 0 is this blue line. Is x-axis, essentially. So that's a linear space. You obviously see that this linear space is contained in R2, because this is just a line going through 0, and R2 is everything around. So we can say that span of vector v here is a subspace of R2, because obviously it's smaller than R2. Span of vector 0, 1, again in R2. What is it? It is a linear space created or generated or spanned by vector 0, 1. So that's a space created by all the linear combinations of vector 0, 1. What are those? But this is just a scalar multiple of vector v, 0, 1. So it's a linear space. Again, it's a straight line that goes through 0. And again, obviously, it is a subset or a subspace of R2. R2 is all around, everywhere. And this guy, for us, span of vector 0, 1 is a blue line. So that's also a linear space. But it's very small, much smaller than R2. That's why we can say that it is a subspace. So span is always a linear space. So this line here is a linear space. We can create another linear space with actually any vector in R2 or R3 or R75. So here vector 1, 1 creates a linear space, again going through 0. Every linear space must contain origin, vector 0, always. So here these are all scalar multiples of vector 1, 1. That's a linear space. Here I have a vector in R3, so x, y, z, R3, vector 0, 1, 1. And I have a span of that vector, which is a linear space, again containing the origin. So 0 must be there, always, always, always. So this is a linear space, straight line through 0. Actually, every straight line through 0 is a linear space. And also, if you have a line that is parallel here and doesn't go through 0, it is not a linear space. We already said every linear space must contain vector 0, must contain origin. Mandatory. If it doesn't, if a set does not contain origin, it is not a linear space, period. So here we have a linear space going through 0 generated by vector 0, 1, 1. In R2, we know that vectors 1, 0 and 0, 1 are standard basis, and they are also linearly independent. We know that. So we can create a linear space with those two vectors. What is a linear space created by those two vectors? But it's a linear space created by all linear combinations of vectors e1 and e2, which is actually here, a1 times e1 plus a2 times e2. For a1 and a2, a1 and a2 real numbers, any real numbers. So every vector in R2 is actually a linear combination of those vectors. Therefore, span of e1 and e2 is actually R2, because every vector in R2 is a linear combination of them. And all linear combinations of them are vectors in R2. So basically, span of e1, e2 is R2. Ah, beautiful. Here we have two vectors in R3, v1 and v2, and they are linearly independent. So they are not scalar multiple of each other. That's what it means. So a linear space created by all linear combinations of vectors v1 and v2 is a plane passing by the origin, by vector 0, 0, 0. And this plane here is a linear space. And again, every linear space must pass by the origin. Here origin is vector 0, 0, 0 because we are in R3. So those two vectors v1 and v2 are vectors from R3. So linear space here is the plane. All linear combinations of vectors v1 and v2. What happens if we have two vectors but they are linearly dependent? Here, an example in R2, we have vector v1 and v2 and they are collinear. Basically, here v1 and v2, so v2 is like negative 1 over 2 times v1, for example. So they are linearly dependent and they are on the same line. Here we have v1 and v2 is some number greater than 1 times v1. So basically what happens when one of the vectors is a scalar multiple of the other? Well, we can still have a linear space. Span of v1 and v2 is a linear space, fine, and in this case it happens to be a straight line through 0. Why is that? Well, we know by definition that linear space is set of all linear combinations of v1 and v2, but they are collinear. v2 is some number times v1. So if we just plug it into the equation here and we shake it a little bit, we will get a constant times v1. So this is a scalar multiple of v1. That's what it is. Oh, somebody can say, oh, but I would like to have v1 equal to 1 over k v2. Okay, no problem. You can replace that and we shake it and we get that actually it's a scalar multiple of v2. So all linear combinations of v1 and v2 are either scalar multiple of v1 or scalar multiple of v2, which is not a big deal because they are collinear, they are on the same line. So when we have two vectors that are linearly dependent, the space generated by them, in this case a line, well, is the same as space generated by only one of them. So I don't need both of them to generate this line. v1 is just enough and v2 is just enough. So this tells us something that we will explore very quickly, and that's how we are going to introduce the notion of a basis. So we have here vectors v1 and v2, and one of them is useless actually to create the space. So span, the space that I generate by all linear combinations of v1 and v2, can be actually generated as a scalar multiple of v1 or as a scalar multiple of v2, your choice. But I don't need both of them, obviously, I just need one of them. So this is something that we are going to exploit later on. So we can say that v1 is too much or v2 is too much. We don't need both of them, we just need one of them because we know already that they are linearly dependent. So basically we can kick out one of them out. Kick him out and then you still get the same space. Amazing. So what happens if I'm, let's say, in R3 and I have three vectors, but v2 and v3 are actually collinear. So v3 is some number times v2. So v3 is some number times v2. So they're linearly dependent. So span of v1, v2, v3 is here a plane going through 0, fine. And it's set of all linear combinations of v1, v2, v3. But since v3 is a number times v2, when I plug it in here, what I get actually is a number times v1 plus a number times v2. I don't need v3, that's what it means. Here, space generated by v1, v2, v3 is the same as space generated by v1 and v2. Similarly, if somebody says, oh, but I would like to express v2 as 1 over k times v3, no problem. And then you bring it into the equation, you shake it, you will get that actually the space that you generate by all linear combinations of v1, v2, v3 can be actually obtained by linear combinations of v1 and v3. So since v2 and v3 are linearly dependent, so they are collinear here, we can kick out one of them. We don't need them. We just need one of them. So space generated by v1, v2, and v3 is actually the same as space generated by v1 and v2, or space generated by v1 and v3, because we can kick out v3 and we are good, or we kick out v2 but we keep v3 and we are good. v1 is linearly independent from them, so v1 needs to stay. But v2 and v3, we don't need both of them, we just need one of them because they are linearly dependent. So this is something that starts bugging us. We can kind of kick out one of the linearly dependent vectors and still get the same space. In this example, again, R3, we have three vectors, and span of those three vectors is a plane going through 0 again, but this time vectors are not collinear, but they're still linearly dependent. So let's say v3 is some linear combination of v1 and v2. So when I go and create the space of all linear combinations of v1, v2, v3, well, I can replace v3 by this expression here. So if I do that and I shake it a little bit and I do a little bit of algebra, what I get is that space generated by all linear combinations of v1, v2, v3 is actually the same as the space obtained by all linear combinations of v1 and v2. So again, one of the linearly dependent vectors, in this case v3, I can kick it out. Obviously, from here, you could say, well, I could express v1 as a linear combination of v3 and v2. Yes, do it, fine. Or you could say, hey, I can use this equation to express v2 as a linear combination of v3 and v1. Yes, you can, fine. What happens in those cases? You again plug which one you chose into this equation here, you shake it, and what you get is, at the end, some constant times v1 plus some constant times v3. Or you get some constant times v2 plus some constant times v3. So basically what we see in this case, where we have these three vectors that are linked by some formula, okay, they're a linear combination of each other, what happens is we can kick out one of them. In this case, we could kick out v3. We could choose to kick out v2, or we could choose to kick out v1. And we would still get the same space. So the space generated by all three vectors, v1, v2, v3, and they are linearly dependent in this case. They are linked by the formula here, but this linear dependence. Well, we can kick out one of them and still get the same space. Which one? Well, whichever one you like, or you don't like, you just kick it out. You get the same space. In the previous case, v2 and v3 were collinear, so only one of them is needed, the other one is not. v1 was independent from them and v1 needed to stay. In this case, it's different. v3 is linear combination of v1 and v2. You could re-express it and say v1 is linear combination of v3 and v2. Fine. Somebody else could say, but wait. This also means that v2 is linear combination of v1 and v3. All of that is correct. So as soon as you figure out which one is linear combination of others, well, you can kick that guy out. In this case, we kicked out v3. Or you can say, I can kick out v2 if I express v2 as linear combination of v1 and v3. Perfectly fine. If I express v1 as linear combination of v2 and v3, I can kick out v1. Fine. So it's up to you. At the end, you'll get the same linear space. So when we have linearly dependent vectors, depending on type of dependence, we can kick out one of them and still preserve the same space. So this brings us to the notion of basis, because there's something deep inside here. We have some vectors that are useless and some vectors that are useful to create a linear space, the span. So the guys that are useless, we can kick them out. So we don't need them. And that's where the notion of basis of a linear space comes. We say that a set of vectors in a linear space, so vectors v1, v2, vk, is a basis for a linear space if and only if both of the following conditions are satisfied. So first thing, all the vectors in the set S are linearly independent. And second thing that must be satisfied also is that the set spans V, which means set S creates V, which means that V is a set of all linear combinations of vectors v1, v2, vk. Okay, so this is pretty much a space. So a basis is actually a set of vectors that are independent and they create entire space. We just need those. So if we go back here, we saw that v1, v2, v3 are dependent. So all three of them, they cannot be in a basis because they are dependent. So we need to kick out one of them. and then the other two are independent. So you see, if we kick out V3, we have V2 and V1, they are independent. If we kick out V2, we have V3 and V1, they are independent. If we kick out V1, we have V2 and V3, they are independent. So we only need two of them. The third one is dependent, we kick it out. So in this case, basis would be V1 and V2, or V1 and V3, or V2 and V3. So what we see here is that actually a linear space can have several bases. It's not just one, it's many, many. So what is important is that the set is linearly independent and creates the entire space. So in this case, that's what happened. Vectors v1, v2, v3, they create the space, but also vectors v1 and v2, and also v1 and v3, and also v2 and v3. So all of these couples here create the same space as these three guys. But these three guys are dependent. So linear dependence is a problem. But v1 and v2 are linearly independent, and they create the space. So v1 and v2 are a basis by the definition. Or v1 and v3, they are linearly independent and they create a space, so they are a basis. Or v2 and v3, they are linearly independent and they create the entire space, so they are a basis. So we see that a linear space can have many, many, many bases. Now what happens here is you see two people. Two linearly independent create a space. Two linearly independent create a space. Two linearly independent create a space. These three guys are dependent, so we don't care about the fact that they create a space, but they are not independent, they are dependent. So v1, v2, v3 cannot be in a basis, obviously. Only two of them. And that's where the dimension, the notion of dimension comes. Dimension is just the number of vectors in a basis. How many vectors are in the basis? In this case, there were only two. So dimension of this space here is 2. Okay? Because there are two people in a basis. By the way, every basis for a linear space has the same number of vectors. We saw that each time we have 2 in the previous example. And by the way, we can have infinitely many bases for any non-trivial linear space. Because if we go back here, if I multiply v1 by 7, and then I have 7v1, v2, they'll still generate the same space, because the span is just all linear combinations. And they are still independent. 7v1 and v2 are still independent. So I can multiply v1 by any number different from 0, I'll get another vector, and keep v2. I'll have different bases each time, but the same space at the end. So that's what it means here. Every linear space will have infinitely many bases, except the linear space 0, which doesn't have a basis, by the way. So what is important here is dimension is just a number of people in a basis. That's all. We can have infinitely many bases for any linear space except for the linear space 0, and each basis has the same number of vectors. That's why it's called dimension of the space. And what is basis is just a bunch of vectors that generate the entire space, and those vectors are linearly independent. So those are vectors that you absolutely need to generate the space, and they are independent. So there is nothing extra here. You don't have useless people, only useful people because they are independent, and they are enough because they create the entire space. So basis is really the strict minimum you need to generate the space, and all of them are independent on top of that. So we remember linear independence of a set. So a set of vectors is linearly independent when none of them is linear combination of the others. So this will be something useful in this case. The formal definition is fine, but this alternative definition is more useful for us now. Set is linearly independent when vectors in the set, none of them is linear combination of others. So all of them are, none of them can be expressed as linear combination of others. So that's what it means independent. So that's something important. if I go back here, we saw that v1, v2, v3, since they are linked by this, we have v3 as linear combination of v1 and v2. So v1, v2, and v3 cannot be in a basis because they are dependent. And here is dependence. One of them is linear combination of the others. So in that case, all three of them cannot be in a basis. No way, because they are dependent. So if I go again to my special linear space span of 0, which contains actually only one person vector 0, and I remember that vector 0 is actually linearly dependent. So this space, this trivial linear space, 0 space, contains only one person. And this person is linearly dependent. Well, for sure this person cannot be in a basis, and this is the only candidate because this space has only one person inside, and that person is no good because it's dependent. So this person cannot be in a basis. So this set actually doesn't even have a basis. So in this case we define its dimension by saying it's 0. It's like has nobody in the basis. So this is very special case, span 0, so 0 space or trivial linear space. It doesn't have a basis and its dimension is 0. Our classic linear spaces are, which is span of 1, so any real number is product of 1 times a real number, and dimension is 1. So again, curly brackets is notation for set, and it is important to keep it. R2, we know that 1, 0 and 0, 1 is standard basis, so span of 1, 0 and 0, 1 gives R2 because every vector in R2 is linear combination of 1, 0 and 0, 1. So 1, 0, 0, 1 is a basis. It's standard basis for R2, and there are only 2 people inside. So the dimension is 2. For R3, well, R3 is span of these 3 vectors here, standard basis. So this is a basis for R3. So there are 3 people inside. So the dimension of R3 is 3. Dimension is just number of people in a basis. That's all. So for Rn, dimension is n because we have n vectors, standard vectors. So Rn is linear combination of n standard vectors with n components inside. Some properties. So this part is really more theoretical, but it's very useful. So we need to learn these things because they are really, really useful for later on. So if I have a linear space of dimension n, which means there are n people in a basis. So here, the information that is known is that the linear space, its dimension is n. So there are n people in a basis. Okay, and then I have a set of n vectors from V. Okay, so set with n vectors. The fact that I know that my space is of dimension n, and I have n vectors here. So that's something very important that helps us produce the following results. If vectors in set S are linearly independent, then they form a basis of a linear space, just because we know that the dimension of a linear space is n, so that means there are n linearly independent people in a basis. And if these n guys from the space are linearly independent, well, they form a basis automatically. Similarly, if those n people create, span the entire space, so the space is span of S, then they are also bases, which means they are automatically linearly independent also. So the fact that you know the dimension helps a lot. So since my space is of dimension n, any set that has more than n vectors is automatically linearly dependent. So we know that if we remember R2, dimension is 2. So if I have 3 vectors from R2, they are linearly dependent. We already saw that before. we have in that case more unknowns than equations, so Ax equals 0 will have infinitely many solutions, therefore the three vectors will be linearly dependent. The same thing if I have 7 vectors with 2 components, so R2 dimension is 2, if I have 7 vectors, I have more vectors than 2, so those 7 vectors are linearly dependent. Similarly for R3, if I have 4 vectors from R3, dimension of R3 is 3, but I have now 4 vectors of R3, those 4 vectors are automatically linearly dependent. We know that. Also, a linear space of dimension n cannot be generated by less than n vectors. The meaning of dimension n means that we have n people in a basis. Those people are linearly independent and we require n of them to generate the entire space. If I have less than n, even though they are linearly independent, I cannot generate the entire space. For instance, in R2, we know that we need 2 linearly independent vectors from R2. But if I have only vector 1, 0, with that vector, I cannot generate everybody from R2. We already saw that. I'll just have a line that is on x-axis. Well, that's not enough to generate the entire R2. Okay, similarly, if I have 2 vectors from R3, even though they are linearly independent, they are not enough to generate R3. They only generate one plane that goes through 0. So if I have less than n vectors, then they cannot generate the entire space. So those things are kind of obvious, but very useful. Again, I have a linear space of dimension n, so there are n people in a basis, that's what it means. And then we say that the largest linearly independent subset of vectors in V contains n vectors, and it is a basis. So this is the same as saying if you have more than n vectors, they are linearly dependent, and your set that has linearly independent vectors, you cannot have a set that has more than n linearly independent vectors, because if it has more, then they are dependent. So the biggest set of linearly independent vectors has n of them inside. And since the linear space is of dimension n, when you have n people that are linearly independent, they form a basis. So this is automatic. And then something similar, the smallest set of vectors that creates V or spans V contains n vectors, and this is also a basis. So if I want to create, let's say R2, I can create it with 2 linearly independent vectors, or 3 vectors, 2 of which are independent, or 4 vectors, 2 of which are independent, or 75 vectors with 2 components, 2 of which are independent. Okay, so when I have span of a space, the smallest set that contains n vectors will generate the space, and it is a basis. So this result in if H is a linearly independent set of vectors in V, and again V is n-dimensional, so the basis has n people. So I have a set that contains linearly independent people, then that set H is contained in some basis of V. Okay, so we know that every basis of V has n linearly independent people. Set H contains certain number of linearly independent people that is less or equal to n. We know already that. So that set is contained in some basis. Basically, I can take, let's say, 2 linearly independent vectors in R3. Those 2 linearly independent vectors are contained in one of the bases for R3. Basically, I can add another vector to create a basis, another linearly independent vector. And again, if set B creates the entire linear space, then that set contains a basis. So basically I could kick out linearly dependent people and then reduce it to a basis. Those are all kind of obvious things just from the fact that we know the dimension. Another theorem that is also obvious here, if I have a set that has some people inside, non-empty means there's at least one person inside in a linear space V. So set S contains vectors from V, and V is a linear space. So if S is linearly independent set, so that means that people who are inside are linearly independent. And then I have vector V that is also from the linear space, but that vector is outside of the span S. What that means is that V is not in the span S. So V is not a linear combination of people in S. Already people in S are linearly independent on themselves, but now I take a vector V that is not inside that linear space span S. So V is not a linear combination of vectors in S. Okay, fine. That's what it means. Not being in span S means you're not a linear combination of people in S. So people in S are linearly independent and V is independent on them. Okay, so the entire gang is independent actually. So that's what it says. So if I take S in linearly independent people, and this is symbol for union, I put them together with the guy who is linearly independent on them, because he's not linearly dependent, he's not linear combination of them. So when I put everything together, I'll still get a big set that everybody is linearly independent there. Okay, I have linearly independent people, and I add another guy that is linearly independent. So I get a bigger gang of linearly independent people. Wow. Similarly, if I take a vector V that is in S, and that is a linear combination of some people in S. So let's say V is 2 times U plus 7 times W. Okay, so it's a linear combination of 2 people from S. Then if I kick out V, so this is eliminating V from S, so I will remove it, then I'll get the same linear space. Span of S and span of S when I kick out linearly dependent guy, well, that's the same linear space. We know that, we already saw it in one of the examples before. We had 3 vectors, one of them was linear combination of other 2, so when we kicked out that guy, we got the same linear space still. So that's what it says, nothing special. So here in illustration, I have 3 vectors. These 2 are collinear, so one of them is a problem. I can kick out one of them and still get the same plane here, still get the same span, still get the same linear space. These 3 vectors, we had also this example, when one of them is linear combination of the other 2, when I can kick out one of those guys and still get the same linear space, so same span. An illustration for the part A, I have 2 linear independent vectors that generate the linear space S here, span S, and then I have somebody who is completely outside that plane. Okay, so I have actually 3 linear independent vectors. So that's all it says. If you have a guy that is not in span of the 2 guys, well, all of them are linearly independent. Wow, really? Not so impressive. Some more properties. There's a lot of properties here. It's all related to dimension and basis. All of them seem actually reasonable and straightforward, but there's a lot of them to remember still. So I have S, a finite set. So finite set means it has finite number of people, like 2, 7, 10, 55, or 10,000 people, doesn't matter. So it's not infinite, that's what it means, finite. It is not infinite, so it's finite number of people. So I have a set with finite number of vectors inside, and he's contained in a linear space that is finite dimensional, which means, let's say dimension of V is like 7 or 11 or 1000, but it's a fixed number. Okay, so they say if S spans V, so that means that if V is span of S, which means V is linear space generated by all linear combinations of people from S. Okay, so that's if S spans V, but S is not the basis. Okay, so it generates the entire space, but it's not the basis. Okay, then S can be reduced to a basis of V by removing appropriate vectors. Well, of course, it already generates the entire space, but it's not a basis. Okay, fine. That means that there are too many people there. There is some linear dependence in S. So if I start removing or kicking out linearly dependent people, at some point I will reduce S enough to hit a basis, to have enough people to be linearly independent now. They'll still create the space, but they'll be linearly independent. So that's what it means. So if you have 5 vectors in R2 that generate R2, then you can remove 3 of them actually and keep 2 that are linearly independent, and they'll create R2. So that's pretty much what it says. Okay, fine, nothing special. Another property, if S is a linearly independent set and is not already a basis, so S has all people that are linearly independent inside, but there are not enough of them to generate V. So S is not the basis. So they are linearly independent, fine, but there's not enough of them to create V. Then S can be enlarged to create a basis for V by inserting appropriate vectors. So basically what they say, you have S that has vectors that are linearly independent, only linearly independent, but there are not enough of them. There's not enough of them to create a basis. So span of S is not equal to V. It's smaller. So what they say, well, you could find other vectors that are linearly independent on the guys in V or in S, and then keep adding them till you reach a basis for V. Okay, fine. So basically, if I have vector 1, 0, that vector is linearly independent. So I can enlarge that. I can put another vector that is linearly independent on this guy to create a basis of R2. So let's say I have 1, 0 and 1, 1. Well, those two are linearly independent. They are from R2. Now that I have a basis. So that's basically what they say. Or you can have vector in R3, let's say 1, 1, 1 and 1, 0, 0. So those two are linearly independent, but they are not enough to create R3. What they say in this theorem here, they say, oh, you could find a third guy who is also linearly independent, so the entire gang of 3 will be independent, and then you will have a basis. Okay, fine, I know that. It seems reasonable. Last result, if I have, again, a subspace that is finite dimensional, okay, so vector space V is finite dimensional, and I have a subspace W. Well, obviously he is also finite dimensional. So if my V has dimension 7, any subspace has dimension up to 7. Okay, fine. And both spaces are equal if and only if they have the same dimension. Okay, fine. So nothing special here. An example, if just to see that actually R2 can have infinitely many bases, just for fun. So we know that dimension of R2 is 2, so any 2 linearly independent vectors from R2 form a basis of R2. So we know that we have our standard basis 1, 0, 0, 1, so span of that is R2, but also let's say vector 2, negative 1, 1, 3, they are linearly independent, 2 of them from R2, so their span is also R2, so they are basis of R2 also. I can have another couple of vectors 0, negative 1 and negative 2, 7, let's say. They are linearly independent. There are 2 vectors from R2, 2 linearly independent vectors. They are basis for R2. They generate R2. Okay, they generate and they are linearly independent, so they are bases. Just to be clear, it's any real numbers, huh? So that's why I put pi and exponentials and radicals, just to make sure that you remember that these components are real numbers, not only cute numbers. Okay, they can be ugly too, and it's just fine. So any two linearly independent vectors from R2 form a basis for R2. Similar for R3, any three linearly independent vectors from R3 form a basis. So we have a standard basis. So span of the standard basis gives R3. But we can have these three vectors from R3 and they are linearly independent and they form a basis also. So how do I know they are linearly independent? Well, I could form a matrix 3 by 3 and compute determinant, for instance. If determinant is different from 0, matrix is invertible, that means the columns are linearly independent. These three vectors the same, I could compute determinant, or you could try to solve Ax equals 0 and see if you have one and only solution, x equals 0. It's up to you. So these three are linearly independent, so they are basis of R3, so the span of these three guys is also R3. So another example, if I just want to see if a vector u belongs to span of vectors v and w. So vectors are given here. So question is, does u belong to span of v and w? Oh, we can see that v and w are linearly independent, by the way, because they are not scalar multiple of each other. So span of u and of v and w, since they are linearly independent, well, the dimension of h, or the dimension of span, is 2 because it's generated by two linearly independent guys. So that's easy. So how do I answer this question? Does u belong to span of v and w? Well, I remember what span is. Span is just all linear combinations of v and w. So the question is actually, is u one of those linear combinations? So is u a linear combination of v and w? Well, what do I need to do? Well, I need to solve the non-homogeneous equation here. I need to find C and D, if they exist. So I just form a mathematical system, apply Gauss-Jordan, and try to solve. Fortunately, there is a solution, -3 and 5, so u is a linear combination of v and w. So that means that u belongs to span of v and w, because span is just all linear combinations. So u is one of them, obviously. So again, as we said, v and w are linearly independent, so there are two guys linearly independent that generate the entire space H. So that's the definition of the basis. So dimension of H is actually 2 because there are two people in the basis. And here are some examples of bases. Obviously v and w. But now we know that u is actually a linear combination of v and w. So you can replace u, you can replace one of those guys, v or w, by u. It's fine, whatever you do. vu, they are linearly independent. And we already know the dimension of the span is of v and w span. The name is h. So the dimension is 2. So as soon as I have two linearly independent guys, well, they are a basis. These two are also independent, they are a basis. By the way, you can multiply any guy in a basis by any number different from 0, and you will have still another basis. So you can have infinitely many bases, as you see, for any linear space. And obviously, H is span of v and w, but also span of 3v and 2w. Also, it is span of v, w, and u. I can keep adding linearly dependent vectors, actually. It doesn't change anything. It's not useful at all, but I can do it. Okay, so this is another exotic way of saying the same thing. So H is span of these three guys. I know already that u is linearly dependent on v and w, so it's totally useless. But fine, there's nothing wrong with it, it's just dumb. That's why we find a basis. What we want is just people who are good enough to generate everything. Okay, in this case it's just v and w, or u and v, or u and w, or one of those weird multiples. Obviously you cannot multiply by 0. If you multiply by 0, get vector 0, and we know that vector 0 is linearly dependent, so the set automatically becomes dependent, so it cannot be a basis. Okay, so be careful, vector 0 can never be in a basis. Another example, if I want to find a basis and dimension for span of 3 vectors. So here are 3 vectors, and I take span, so this is linear space generated by all linear combinations of these 3 vectors, called W now, and I want to know what is the basis of W and what is the dimension of W. Well, maybe they are independent already, maybe they're not, I don't know. So what I could do is, since I have 3 vectors with 3 components, I can form a square matrix 3 by 3 and compute the determinant. Here the determinant is computed quickly, is 0. What does it mean? That means that the matrix is not invertible. Okay, fine, but what that else does it mean? It means that the 3 columns are linearly dependent. Oh, so all 3 vectors together, they are dependent. So they cannot be in a basis, all 3 together. Somebody needs to go. So vectors, all 3 vectors together cannot form a basis, that's for sure, because they're dependent. I need to kick out somebody. Then I check who should be the victim. And I see that any group of 2 vectors is linearly independent because they're not scalar multiple of each other. So actually I could take any 2 guys together and have a basis. It's fine. So I can have these 2 or these 2 or these 2. I just need to kick out one of them. Because I know 3 together are dependent. So I need to kick somebody out. And I discovered that any 2 are independent. So okay, I can kick out one of the guys arbitrarily and it's fine, the other 2 are independent. So obviously dimension will be 2 because basis is formed by 2 people, so dimension is 2. Which one you choose, well, it's up to you, doesn't matter. You have infinitely many bases anyways, all I need is one of them. So I know that W is span of these 3 guys, but since they are dependent I can kick out one of them, and then it's also span of these 2 or span of these 2 or span of these 2. To help settle these ideas, there are a couple of exercises you can go through just to make sure that you revise the definition and some of the results that we saw. This will help you a lot just to digest the material. In the white book, you see that you have only a couple of problems related to this topic. So topic of just linear space in general, subspace also in general. We will have a special lecture on how to prove that something is a linear space or how to prove that it is not. That's a completely different topic. For now, all we need is just a definition. And then, how do I form a linear space from a linear combination of some vectors? So, creating a span of vectors. And how do I find a basis and dimension? And you see in yellow cover book, you have much more examples and exercises to solve. This will actually help you much more. So I suggest that you actually do both if you can, but if not, you can focus more on yellow book because it has more exercises. So it will help you digest the ideas.